So, today, picking up a little bit where we left off. So I had posed one question to you guys at the end of the notes yesterday. And I asked you guys, when is the projection of U onto V equal to the dot product of UV? Did anybody notice this occurring in the homework last night? Should have happened a couple of times, I think, right? Anybody with any intuition as to why or when this will happen? Because it would be nice, right? Because the dot product's pretty easy to calculate as opposed to the projection, which is considerably more, or the magnitude of the projection, which is a bit more to do, right? Oh, yeah, that's an enormous. Interesting. Okay. Well, can somebody give us an instance in when this happened? All right, well, let's use this instance, right, from the homework, or from the notes yesterday. And see if we can sort through this. Oh my goodness, what just happened here? Okay. So let's look at this. So I'm just going to borrow this problem from yesterday. I'm going to write it this way, I think. Okay. So what was specific about this problem in the example from yesterday? What was the magnitude of H? That was 1, right? And remind me again, what does the dot product result in? It gives us a scalar, right? So because that's a scalar, I can pull that scalar outside of my magnitude. Right? If something is 3 times the length of it, I can figure out the length and then multiply it by 3, or I can measure the whole thing. But I'll get the same answer either way, right? So that's why it's okay to pull that scalar out. And then what's the magnitude of h have to be? How did we calculate h? This is how we got h. So what is h really? Well, okay, but if I think about this cosine comma 335 comma, or cosine 335 comma sine 335. That's a point on the unit circle, right? What's the radius of the unit circle? 1. So what's the magnitude of this vector then? One, right? So this is my vector whose terminal point is on the unit circle. It's got to have a length of 1, right? Ben?
Yesterday you said when you're finding the magnitude of age, you said
right.
So why wouldn't that always be 1?
Because sometimes you can't, sometimes you're given information, you can't pick it to be 1. Yeah, so we only looked at one story problem example yesterday where we had the freedom to do that. Not in every case the constraints will be such to where you can just pick the length for that vector you're projecting onto. But when you can, pick 1, because look at the huge shortcut we get out of this. So the answer to this question is okay here. I have a PowerPoint here that we're going to walk through. Where is that at? I think it's here. Yeah. Okay. So we did a variation of this problem already, right? This is what we did in the notes yesterday. Should we walk through this again? Okay, that's fine. We can do that again. You just have to answer a question, right? Like yes or no. I don't want to waste our time, but if you think this will be helpful to see this again, we can certainly do it again. We have time to do that right now. Okay. So it says Tommy is going sledding on a hill with a 20-degree angle of incline. Tommy and the sled weigh a total of 135 pounds. what is the amount of force Tommy will be sliding down the hill? So this is basically the same problem as what we saw yesterday in the example, just some numbers have changed. So I've started by drawing a picture kind of the situation, right? Whee! All right, so our plan here is we need to define a vector to represent the force affecting Tommy, which is gravity, and then a vector to represent the direction that he will be traveling in. That's the hill. So this is the Tommy vector. That's the hill vector. Everybody okay with that? And this is what we drew in the notes, right? So the magnitude of the Tommy vector is 135. That was just the weight of him in the sled. And its direction is 270 because if we embed like an XY axis, we have that angle there, which was 270. Right? Everybody kind of remember that? And the magnitude of V, we weren't given any information about the length of this hill or how long it is or anything like that. So we have a lot of freedom here to choose the magnitude of the hill to be really whatever we want. What we really care about from the hill is just its direction. So we're going to choose the magnitude to be 1, and the direction is -20 or 340. Either way of writing it is fine. Everybody's okay there? So I'll resolve the vector u, the Tommy vector, into a component form, and then do the same thing for my vector v. Okay. And now, with what we've just kind of pointed out to ourselves, what's the shortcut available here? I can just take the dot product of u and v, and that will give me my answer. Now, I'm not going to do that here, because you can't always do that. But because the magnitude of v is 1, we're able to make that shortcut. We're going to see in some examples here in a moment that that is not always available to us. But here it is. Okay. So there's my dot product. There's v squared, or the magnitude of v squared. So my projection gives me this. And when I take the magnitude, I get that dot product all over again. Now there's some steps that I didn't write down in here, like how I found the magnitude, or this scalar multiplication that I did here, or whatever. Are we clear as to what happened? And I can post this PowerPoint too if you don't want to write everything down. That's not a big deal. Sure, we can do that. Not a big deal. Happy to do it. Everybody's okay? So this is what we already answered, right? So read through this one. Is this any different than the previous example? No, this reads identically, right? Just different numbers, and like we have replaced Tommy with a girl, but okay. So again, we'll find our vector u and v, and we get our projection, and we get our magnitude. Really, though, this magnitude is just the dot product of u and v. Everybody okay? So let's see an example here where that's not the case. So here we have a crate is being pulled up a ramp at an angle of 25 degrees with a force of 75 pounds. If the angle of the ramp is 10 degrees, what is the force that the crate is moving up the ramp? This problem now is decidedly different, right? How many vectors do you hear when you read this? There are three. There are three vectors here that you should see when you read this. One vector is the ramp, right? Everybody okay with that? Okay. Notice, do we know anything about the length of this ramp? So what can we assume the magnitude of the ramp vector to be? 1 step. Okay. Oh, sorry, this is the ramp vector, the 10 degrees. My apologies. Okay. So there's my 1 vector. Everybody agree with that? Okay. We have a weight on an object. That's a second vector. Right? Just like Tommy in the sled. Right? And then we have a third vector that's pulling this crate up the hill. So there's 3 vectors going on here. Does everybody kind of see that now if we point it out to you? Hopefully you'd recognize another story problem that formatted in a similar way that might have 3 vectors going on as well. Bella?
Okay, just to confirm, so the first vector is the one at 25 degrees, and I got the second one below.
No. The first one is the ramp at 10 degrees.
Okay, then what's the second one?
The second one is the mass.
Okay.
And the third one is this pull.
Oh, okay.
Okay?
So vector's not always degrees.
I mean, that's what we had in the previous one, right? We had a vector for the hill and a vector for the mass,
Okay.
right? That's what we saw in the previous ones. Okay. So the plan here then, if I want the force moving up the ramp, I have to do 2 projections. I have to project the mass onto the ramp, and I have to project the pull onto the ramp. Okay? Are these 2 forces going in the same direction or different directions? What direction is gravity going to be acting on a ramp? Is it going to be pulling the thing up or pulling it down? Down. What is the other vector, or what is the other force doing? Pulling the crate up or down? Up. How did you get up? Literally says it in the problem, right? Everybody's good with that. So, because these 2 forces are acting in opposite directions, when I find these 2 projections, should I be adding their magnitudes or subtracting? Subtracting. Okay, which one should I subtract from which? Which one is going to be a positive force and which one is going to be a negative force? The pulling up should be the positive. The pull down from gravity should be the negative. Everybody agree with that? So that's going to be my plan. Everybody okay there? Okay. So, here's my, oh shoot. This one is, oh my gosh, guys. Okay. I am on a different example. It'd help if I read this thing more carefully. What this 75 pounds, is this the mass of the crate? Read the problem. No. So everything I just told you doesn't apply here. I know. You ever like read something and you just kind of skim through it because you know what you're expecting, and then it turns out that like, oh no, that's not the thing I should have been reading right now at all? That's what I just did. So let's start over. What I said to you will apply. It's just not yet. Okay? So there are two forces going on here. There's the pull and there's the ramp. Okay? This is the pull vector. This is the ramp vector. We did it the same way. Yes or no? Yes. Do we know anything about the weight of the crate? No. So we can assume that to be basically 0. Okay? So it's not going to make any impact here. So the projection here, how can I find the magnitude really easily? Just take the dot product, because the magnitude on V, the ramp, we would have chosen to be 1. Yes, Olivia? I did like cosine of 25 times 75, and then cosine of, or sine of 25 times 75. And then this is cosine of 350 and sine 350. Is that okay?
Yeah.
My apologies there. I got ahead of myself. Benji.
You're not drawing the graph.
So we have a force going up at an angle of incline of 25 degrees.
Can't see that.
Oh, that's weird. And then I have the ramp that has an angle of incline of 20 degrees. Oh no, wait a minute, hold on, I'm sorry. Jeez, cheapers creepers. Come on, Mr. Kulik, stop making a mess out of this.
It is 10 of it.
Oh yeah, 10, thank you. So that's what's going on.
And then it's lower the weight.
Huh?
The weight.
There is no, the force is that's for the magnitude of U.
So we don't put that on the graph.
You don't need to include that. I mean, it's basically means it's like how long this is.
Okay.
But we don't really need to draw this to scale to do this. So I wasn't really worried about it, if that makes sense. If it was drawn to scale, you know, this one is like 75, and that one's like 1.
Yeah.
So it's like you can't even really see them at the same time. So, you know what I mean?
Yeah.
Okay. Yeah. So there's 25, and then this one's like 10. So if I did this, then U would be 75 cosine of 25, comma 75 sine 25. And Olivia, I misspoke to you early. This would just be cosine 10, sine 10. My apologies. Again, with the magnitude of v being 1. And because we have that, we can just find the dot product to get our answer. Does that feel better? Okay. Yeah. And if there's places where we need to fill in,
Yeah.
like, feel free to stop me and ask, and we can certainly do those sorts of things. Sure.
The other problem, one of the vectors was 0, and like the negative weight, why was that?
So here, this 75 pounds is not a weight. It says it's a force. So it's part of this pull. It's not a weight. So forces can be measured in pounds. Does that feel good? Okay. If it was the crate weighed 75 pounds, then it would be a vector itself, and a pull, and a ramp, all three being vectors. That's what I initially had thought this example was, but that one comes later. I just got ahead of myself. Okay. Did it do it? What did it do? There it goes. Can I say for the record, like, I hate the new version of PowerPoint that, like, when you have a monitor projecting somewhere else, it wants to do like all kinds of weird stuff. Just as a separate aside. Jackie, what were you going to ask?
So after you get the vector,
We can do the dot product here because the magnitude for the vector v, the ramp, is 1 still. So we can still do that. You could find the projection and get the magnitude of the projection also. That's never going to be wrong. It just may not be the shortest way to do it, but it's never going to be wrong. And there's going to be cases where we can't do the dot product. I think the next example is going to be that case. Yes. All right, ready to move forward? This one says a crane is pulling a ramp or crate up a ramp with a force of 86 pounds at an angle of 19 degrees. That's one vector right there that I read, right? It says the ramp extends 7 feet horizontally and ascends 1 foot vertically. That's a second vector. How much force is the crate moving up the ramp? So again, just 2 vectors. We're going to project the pull onto the ramp. How am I going to find the vector for the pull? (86 cosine 19, comma 86 sine 19). Just translate that vector to component form. Everybody happy with that? Okay. What's the vector for the ramp going to be? In component form, it's very easy. It's 7, 1. Because you went 7 units to the right and 1 unit up. Is the magnitude of V 1 in this case? No. Can we use the shortcut of just taking the dot product? No. Here we have to find the projection vector, and then we have to find the magnitude of that vector afterwards. Everybody see the kind of story problem format in which you'll have to find the full projection? So you'll have to know something about the length of the ramp or the dimensions of the ramp or something. Okay? So here's the projection that you should get. And when we find the magnitude, we get this. Worth noting that that will never be, that is not the same thing as what the dot product was. Okay? The dot product was more. Is that okay? If you still wanted to try to do the dot product shortcut, what could you do to this problem first in order to use that? It's using a technique we did in the first section. Yeah, if I make v a unit vector in the same direction, I could then use the dot product shortcut. Do you remember how to do that? You just multiply v by 1 over its magnitude. So in this case, if I took and used v as 7 over the square root of 50, 1 over the square root of 50, that would work. There you'd have a unit vector there, and you could use the dot product shortcut. To me, that's really not any faster than doing this, but it would be fine. Brockton? So it's the square root of this thing squared plus this thing squared. That's just the formula for magnitude. Does that ring a bell? Okay. So remember, the vertical bars around the vector mean magnitude. Calculating the magnitude in component form is easy. You just the square root of the component squared. Or the square root of the sum of the component squared. Excuse me. Is everybody okay here? So again, our answer then we'd say is about 84.46 pounds. Okay. Last example. God bless you. Okay. So this is asking about 3 forces, right? We have the angle of incline for the magnum. That is one vector. It says if the combined weight of the car and its people is 7,000 pounds, that's our second vector. And then it asks how much force is required to keep the car from slipping backwards down the hill. So the roller coaster needs to be exerting some pulling force up to pull this car up the ramp or up its, whatever, its hill or whatever, right? So this is kind of the scenario that we described before. So whatever that force is, minus the force that gravity is projecting onto that ramp, should give us something greater than 0. Needs to be greater than 0. Does that feel okay there? Okay. So I'm going to resolve these into 2 vectors. So here is the weight of the roller coaster car, And here is the ramp vector. Notice we don't know anything about the ramp vector, so we can pick it to have a magnitude of 1. Yes, Ben?
What's the magnitude of,
Well, I mean, it's 7,000. So we can calculate the projection and find its magnitude, or just take the dot product of these two vectors since v has a magnitude of 1. Now, is this force negative or positive? Gravity is the force that this is coming from, right? Pulling the car, which direction? Down, so this should be a kind of a net negative force. So how much force would we need to act against it to keep the car from falling backwards? Physics students, how much? So this 4,499.51 is a force pulling down the ramp. How much force do we need moving up the ramp to keep the car from falling backwards? Nope. How about 4,499.51? It should be equal, right? Because then they're going to cancel out and nothing's going to go anywhere, right? So it should be at least that much. Yes, sir. Cosine 40, sine 40.
Oh, times the 1?
Yeah. Yep. Sure.
So the x of 0, you got that from saying that it started at the bottom instead of the origin.
Well, that would be like 7,000 times cosine of 270. So gravity is always going to be going straight down. So it's just going to be negative in the y direction with the 0 and the x kind of every time. But acting straight down is the same as a 270-degree angle.
And then you did 7,000 sine of 270.
Yeah. Yeah, exactly.
Oh, so this is like basically what we did the other day.
Yeah. 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 Okay. Yes, sir. Of course. Okay. Last example. Did I say that earlier?
Yeah.
I lied. Take a read through. Tell me how many vectors. There are 3. What are the 3 vectors for? One of them is the weight of the crate. Good. What else do we have? The ramp. Very good. And the pull. Yeah, the force pulling up, right? Everybody agree with that? Okay. So just like what I had said in the beginning that I didn't mean to say, this is the problem I was thinking of. So we have three forces. We have to project the force of the crate pulling down because of gravity onto the ramp, and the force of the pulling up onto the ramp, and then find the difference of them. Okay? So we have the weight of the crate down the ramp. We have the force of the crane up the ramp. And then the final answer is going to be the force pulling up minus the weight pulling down. So if we have a positive direction, the crate should be moving up. If it was negative, it would still be sliding down. The crane isn't doing enough work to keep it. You know what I mean, guys? Okay. Everybody good with the format there? So, to find the weight of the crate down the ramp, I have the weight of the crate and the ramp vector. What's the magnitude of V? 1. Nowhere in here do we specify a length for the ramp. So what can I use here? The dot product shortcut, right? So when I do that, I get about 25.88. Bella, what's your question?
For you, or just like in general, I just want to make sure I'm doing it right to get those numbers.
That's
So
fine. You can ask.
do 1 times cosine of 100 and sine of
270.
270.
100 times cosine 270 for you.
Where did you get 270? Is that just like the math?
It's if you're pulling down, if you draw the xy axis, the vector is pointing straight down on the negative y axis, right?
Yeah, which is
Measure from positive x to negative y is
Okay.
270 degrees.
So it's 1 times cosine of 270.
100, because the
Oh, yeah, that's
magnitude
what I
is 100.
Yeah.
Yep.
Okay, so then for V,
hmm
that is 1 times cosine of 150. I don't know. Yeah, this is
15.
Okay.
So the angle of the ramp, I'm going to use to find the ramp vector. I'm going to use the angle of the pull to find the pull vector. And then the angle from gravity is always 270. Gravity is always pulling straight down. I guess unless you're in space. But
We don't have it.
we won't have any space problems. But if you're a physics person, you could certainly have space problems. But if you're on the surface of a planet, the major force is the mass of the planet, which is acting straight down. If you're out in space, it's a different story because now space is curved because of the mass of these planets or stars or whatever, and gravity behaves a bit differently. Everybody happy with this? Now do the same thing for the crane projected onto the ramp. So my crane vector is 150 cosine 35, or 150 sine 35. And my ramp vector is still the same. Since vector v here, the vector we're projecting onto, its magnitude is still 1. We could use the dot product shortcut here. When we do that, we get 140.95-ish. So my final answer is going to be the 140.95 minus the 25.88 to get me 115. Still 15 minutes. So you notice that we didn't talk about any of the questions from last night's homework. I assume there was going to be kind of a lot of them. Do we feel any better about these processes after doing things today? I intentionally didn't check it because I anticipated having like the story problems basically blank for many of us, which is fine. Hopefully you feel better to where you could feel like you can do those. I would say for tonight, if you can do through 50, so there's the 6 story problems there. Hopefully you're able to do just the projection calculations relatively easily, as it's just applying a formula there. But if you couldn't do 45 and 46, you should try to do those. And then I'm adding to it 47 through 50. Sam?
So for the force of crane upright, what was W? That was cosine times 0.01.
So this is 150 cosine 35, 150 sine 35.
Okay.
So that's the ramp stats, the direction and magnitude. I'm sorry, the crane stats.
All right.
Is that cool?
Yes, thank you.
Yeah, you're welcome. And then next time, tomorrow, I guess, since this is the second hour, we'll take questions on 41 through 50 there.
Well, is this gonna be like a super long test? There's a lot of stuff.
There's a lot of stuff. I'm going to be picky about kind of what I put onto the test, and we'll be clear beforehand kind of what to expect. So it'll be either, if it's a lot of things, they should be simple things, or they might have few kind of harder things. But I'm realistic about what you're able to do inside of a normal testing day. Yeah. But yeah, there's a lot of content in this chapter.